All right, we can totally do a second derivative test. All right, we can do a first derivative and we can do our second derivative test. So the second derivative test tells us concavity and inflection points. All right, so if I have a graph, all right, let's talk about what these different things are. With this graph, here where I change, so I've got from here up, right? And I've got from here, let's change back to pink, down. This is concavity. If it's going like this, that's going to be concave up. If it's looking like this, right, that's kind of cupped down, that is concave down. Oops, I should do my arrow the other way. Where you change concavity, all right, so where this graph changes in concavity right here, that is an inflection point. And those are the critical values in the second derivative test. All right, you still find critical values exactly the same way. Where is it undefined and where does it set equal to 0? Those are critical values. Okay, so let's try this thing out. Now we know what concavity is. Let's do an example. So here's example 7. We want to use the second derivative test of my function f of x is equal to 3x to the 4th minus 4x cubed minus 6x squared plus 12x plus 1, right? Look familiar? It should, because we just did it. So my first derivative is 12x cubed minus 12x squared minus 12x plus 12. And what we did with the first derivative test is we factored it, right? Now here's my question to you. Yes, we factored this because it worked really well to find critical values. However, what am I going to be looking at whenever I try to do a second derivative? Do I want to look at the factored form? No, right? So in order to get the second derivative, we are going to look up here at the polynomial, and then I'm going to take my second derivative from that. So we've got 36x squared minus a 24x minus 12. Right? Okay, that is what we now factor and figure out how we're going to pull this off. I'm going to get out of red here. So let's factor this. Oh, what's in common? A 12 again, which leaves me with a 3x squared minus 2x minus 1. Oh, well, we can factor that, no problem. I've got my 12, I've got a 3x and an x. 1 in the back is my only choice. I want a negative 2 and a positive. So here I have negative 3 plus 1 is that negative 2. Nice and factored. So then I look at my critical values because I'm going to set this equal to 0. So x is a negative 1/3 and x is a positive 1. Those are my critical values. Now again, if it were in the denominator or something happened there, we could still use those as critical values. That's no problem. All right, but this is just a polynomial, so I know I don't have to worry about anything undefined. I'm going to scoot this up so we can still see our derivative here that's factored, because this is the nice one to plug into. Same thing. We're going to do the same chart. We've got an interval. But this time, I want to know where my second derivative is either positive or negative, and that tells me, is it concave up or down? All right, and then where it changes concavity, that's where you can find that inflection point. So around all of them, negative infinity to a negative 1/3, negative 1/3 to 1, and from 1 to infinity. Let's see here. So again, nice easy values. I'm going to take my second derivative of negative 1 and plug that in to my second derivative because that's what it's asking for. So if I plug in a negative 1 there, I'm going to get negative. Negative 1 there is more negative. So negative times a negative is a positive. So that tells me concave up because it's positive. All right, let's go something nice and easy. How about a 0? If I plug in a 0, then I've got 1 times negative 1. So positive times a negative. That tells me concave down. Oh, what's a nice easy one there? 2 is what I'd go with. So plug in that 2. So that's positive, and 2 is bigger than 1, so that's also positive. So positive times a positive is a positive, and I'm going to go with concave up, right? So this is showing me that I'm going to go for concave up to concave down. What's happening right there? An inflection point. So at x is equal to a negative 1/3, I have an inflection point. So if I'm going to go from concave down, right, to concave up, what's happening in between there again? Another inflection point. Good. Flexion point. Man, my handwriting's super bad. Inflection point is what I have. That's an NT. All right. So your first derivative test, you're getting your maximums, you're getting your minimums. Is my graph increasing or decreasing? So not only do I know max and min, but more importantly, I know if my graph is increasing or decreasing. You have to give all of that information on the first derivative test. On the second derivative test, you were telling me, is my graph going to be concave up or concave down? All right, and if it changes concavity, that gives me an inflection point. The first and second derivative tests tell you the behavior of the graph. So we need to get real good at this because we're going to use all of these characteristics to actually make graphs. That's coming up next. Ooh, it's so exciting.